Next, let's share the process routes for BC cells. First, an introduction to BC cells. What is a BC cell? It is a full back contact cell with no front side grid lines. All grid lines are placed on the back side. Since the front side has no grid lines, there is no shading, maximizing the utilization of incident light. Its improvement lies primarily in structural modifications, moving grid lines from the front to the back, enabling the stacking of additional cell layers and integration of different passivation techniques. For example, if combined with a tunnel oxide and polysilia, it becomes a TBCCELL. If amorphous silicon passivation is used, it is termed HBC. For p-type composite passivation technology, it is called HPBC. In summary, variations of BC cells are extensions based on different passivation methods. Next, let's take a look at the cell structure. Let's start with the cell structure. Look at the back side, where the emitter in the P region and the N region form an interdigitated shape. The back side has the positive and negative electrodes like this. Now, let's look at the cross-sectional view. The top layer is a silicon nitride structure. Here, the refractive index of silicon nitride is variable, marked as X. We can control the refractive index by adjusting the flow ratio of silane and ammonia. If we want to increase the refractive index, we reduce the ammonia flow. If we want to decrease it, we increase the ammonia flow. So, what's the purpose of controlling the refractive index? Firstly, high refractive index silicon nitride can bond with more hydrogen atoms. More hydrogen atoms mean more free hydrogen, which is useful for bulk passivation. Secondly, low refractive index silicon nitride has an advantage in anti-reflection, which can enhance the optical anti-reflection effect. Below the silicon nitride is a layer of silicon dioxide. What does this silicon dioxide do? Notice there's a slight doping here. This doping is called impurity introduction. There are two types of doping: interstitial doping and substitutional doping. What we want is substitutional doping, where phosphorus and silicon form a chemical bond. This is the active doping we need. The other type is when two atoms just stay close together, which is useless doping. This kind of doping introduces defects and captures photogenerated carriers. When making silicon dioxide, it combines with interstitial phosphorus passivation to form chemical bonds, which helps with passivation. Since phosphorus is a pentavalent element with 5 outer electrons, its majority carriers are electrons. When electrons diffuse, negative charges move, leaving holes. The positive and negative charges form a built-in electric field, which helps separate carriers and prevent them from recombining. This is the function of the front field. Then there's doping in the bulk region and the back. What does heavy doping do? The N region is heavily doped with phosphorus. The more doping, the lower the resistance. So, we use heavy doping to reduce the resistance and mainly to minimize electrical losses. This is the P region emitter, as well as its back film and metal electrode. Most BC cells use N-type substrates. What are the advantages of N-type substrates? Firstly, they have a higher minority carrier lifetime. For P-type substrates, the minority carrier lifetime might be in the tens or hundreds, while for N-type substrates, it can be as high as several thousand. A higher minority carrier lifetime means high efficiency. For example, the efficiency of PERC cells is around 21%. Secondly, N-type substrates have a higher bifaciality. That is, a higher bifacial light emission rate than P-type substrates. There are also other advantages, such as higher mechanical strength, greater tolerance to metal impurities, and stronger resistance to defects. After talking about the advantages of the BC structure and the substrate, let's look at its process flow. First, the N-type raw silicon wafers are cut and then go through a cleaning process. What's the purpose of this cleaning? There are mainly 3 points. First, when cutting the silicon rod into wafers, it causes surface damage. So, the first step is to remove this damage because these damaged areas are defects that can capture carriers. Second, we need to form a textured surface to reduce reflectivity and enhance light absorption. Third, we need to remove oil stains and metal impurities on the surface. These are the main purposes. Next is boron diffusion. In BC cells, diffusion is necessary, and it's done on the backside, so it's called back boron diffusion. Then what's the purpose of depositing a mask? The main reason is that the solid solubility of boron and phosphorus in silicon is different. The solid solubility of boron is about half that of phosphorus. So, it's more difficult to do boron diffusion. For example, when doing phosphorus diffusion, we first form a pre-oxide layer to slow down the diffusion process. But for boron diffusion, we don't need to do this because it's already difficult to diffuse. Also, the subsequent driving-in temperatures are different. Phosphorus diffusion can be completed at around 800 degrees Celsius to achieve the desired surface concentration and junction depth, while boron diffusion requires a temperature above 1000 degrees Celsius to get an ideal effect. This is due to their different solid solubilities. When doing boron diffusion, we usually make the layer slightly thicker. This is because of the different segregation coefficients. The segregation coefficients of boron and phosphorus in silicon and silicon dioxide are different. For boron, it's 10:3, and for phosphorus, it's 10:1. What does this mean? It means boron prefers to stay in silicon dioxide, while phosphorus prefers to penetrate into silicon. So, we use a slightly thicker BSG layer to absorb unwanted defects through interstitial doping, forming a dead layer and a boron-rich layer that can be easily washed away. These are the differences in the fusion. Then, laser grooving is used to create a gap region for isolation to prevent short-circuiting. Finally, another cleaning is done to remove unwanted substances such as excess masks, phosphosilicate glass, and borosilicate glass, forming a pattern structure. Finally, silicon nitride is deposited on the front and back sides, and then screen printing is carried out. This is the IBC process route.